does not move. Its roof has been continuously thatched. A properly installed thatched roof achieves. The objection arrives immediately, reliably. A typical water-reed roof contains archaic resilience.
Chapter 1. The Roof That Defied the Storm. Somerset, England. February 1990. A storm system designated Daria by meteorologists tears across the British Isles with sustained winds exceeding 160 kilometers per hour. Trees older than nations snap like kindling. Power lines collapse. Modern roof tiles, ceramic, concrete, composite, rip from buildings and become airborne projectiles. Insurance claims will eventually exceed £2 billion. In the village of Stoke St. Gregory, surrounded by the wetlands of the Somerset Levels, a man named William Carew stands in his doorway and watches the apocalypse unfold. His neighbors' houses are losing their roofs in real time. Modern tiles peeling away in sheets, felt underlayments shredding, rafters exposed to driving horizontal rain. His own roof does not move. It does not shift. It does not lose a single straw. William's cottage was built in 1437. Its roof has been continuously thatched, repaired and renewed in layers for 553 years. The current surface layer dates to 1962. The base coat, the compressed foundation of straw that forms the structural core, contains material carbon dated to the late 16th century. 400 years of accumulated thatch pressed into a mass so dense that it functions as a single organic unit. The storm hits it with everything modern construction materials cannot withstand. The thatch absorbs the impact. Individual straws flex. The surface ripples like the coat of an animal in wind, but nothing tears. Nothing lifts. Nothing fails. When Daria finally exhausts itself over the North Sea, William's roof remains exactly as it was. His neighbors spend months under temporary plastic sheeting, waiting for contractors, filing insurance claims, arguing with adjusters. William makes tea. He has lived under this roof for 43 years. His father lived under it before him. The roof has outlasted empires. It will outlast him too. Chapter 2. The Anatomy of a Forgotten System. A thatched roof is not a primitive covering. It is an engineered system of extraordinary sophistication, developed across millennia of trial and error, refined to a precision that modern building science is only beginning to appreciate. The foundation is the roof structure itself. Rafters typically set at a pitch between 45 and 55 degrees. This angle is not aesthetic preference. It is hydraulic engineering. Rain striking a surface at this pitch cannot penetrate. The water's kinetic energy drives it downward along the straw stems faster than capillary action can pull it inward. Shallower pitches allow water to slow and seep. Steeper pitches create turbulence that forces water under overlapping layers. The 45 to 55 degree range represents an optimization window discovered through centuries of building failures and successes. Above the rafters, a system of horizontal battens creates the framework for thatch attachment. The spacing of these battens varies by region and material. Closer for fine wheat straw, wider for coarse water reed, but always follows a ratio calculated to provide secure fixing without compressing the thatch so tightly that it loses its insulating air pockets. The thatch itself arrives in bundles called yelms, each containing thousands of individual stems aligned in parallel. Butts facing outward, tips facing inward and upward. A skilled thatcher places these yelms in overlapping courses, each layer concealing the fixings of the layer below, creating a continuous surface with no exposed attachment points where water could penetrate. The cumulative thickness depends on material and regional tradition. Water reed roofs in Norfolk might measure 12 inches at completion. Long straw roofs in Devon could reach 18 inches or more. This thickness is not decorative excess. It is thermal engineering of remarkable effectiveness. Chapter 3. The Physics of Warmth Without Fuel. Modern building science obsesses over R values, measurements of thermal resistance indicating how effectively a material prevents heat transfer. Contemporary insulation standards typically require R values between 30 and 60 for roof assemblies, achieved through manufactured materials like fiberglass bats, spray foam, or rigid board insulation. These materials did not exist before the 20th century, yet medieval buildings remained habitable through winters that killed exposed travelers within hours. The secret was thatch. A properly installed thatched roof achieves R values between 40 and 50, exceeding modern code requirements, using nothing but dried plant stems and trapped air. The mechanism is elegant. Each individual straw or reed stem is a hollow tube, its interior filled with air. When thousands of these tubes are bundled together, they create millions of tiny air pockets separated by thin walls of plant fiber. Air is an excellent insulator. Its thermal conductivity is roughly 25 times lower than concrete, 10 times lower than wood. But air only insulates when it cannot move. Convection, the circular flow of warming and cooling air, transfers heat efficiently. The genius of thatch is that its structure prevents convection while maximizing air content. Each stem's hollow interior is too narrow for significant air circulation. The stems themselves, packed tightly but not crushed, create tortuous pathways that resist air movement between them. The result is a roof that traps body heat, fire heat, cooking heat inside the building during winter, while simultaneously blocking solar radiation during summer. Thatched buildings maintain remarkably stable interior temperatures year-round, without mechanical heating or cooling. Medieval inhabitants did not understand thermodynamics. They understood that thatched houses stayed warm when it was cold outside and cool when it was hot. They understood that stone-roofed buildings required constant fires, while thatched buildings needed only occasional heating. They understood, through generations of lived experience, that thatch worked. Chapter 4. The breathing barrier. Here is a problem that modern construction has never adequately solved. Moisture management. Human activity generates water vapor. Breathing, cooking, bathing, simply existing. This vapor migrates outward through building assemblies, seeking equilibrium with drier exterior air. When vapor encounters a cold surface, the underside of roof sheathing in winter, for example, it condenses into liquid water. That liquid water saturates insulation, reducing its effectiveness. It soaks into wood framing, promoting rot and mold. It drips onto ceilings, staining and eventually destroying interior finishes. Modern building codes address this problem through vapor barriers. Plastic sheeting installed on the warm side of insulation, intended to prevent moisture migration entirely. The theory is sound. The practice is catastrophic. Vapor barriers must be absolutely continuous to function. A single tier, a mist seam, a penetration for electrical wiring, and moisture bypasses the barrier, concentrates at that location, and causes localized damage far worse than distributed moisture movement would have produced. Study after study documents modern buildings failing from moisture damage within decades of construction, their sophisticated vapor management systems defeated by inevitable imperfection. Thatched roofs approach the problem differently. They do not attempt to stop moisture movement. They accommodate it. The thatch assembly is permeable. Water vapor passes through the millions of air spaces between stems, reaching the exterior surface, evaporating into the atmosphere. The roof breathes, just as traditional lime mortar walls breathe. Moisture never accumulates because moisture is never trapped. The plant stems themselves are hygroscopic, absorbing and releasing water vapor as conditions change, buffering interior humidity fluctuations. A thatched building maintains relative humidity between 40 and 60% year-round, the range most comfortable for human occupancy, most protective of wooden furniture and structural elements, most hostile to mold and dust mites. Modern buildings swing between winter dryness that cracks wood and irritates respiratory systems and summer humidity that promotes biological growth. Thatched buildings self-regulate. Chapter 5. The Water Reed Masters of Norfolk. The Norfolk Broads, a network of rivers, lakes, and marshes in eastern England, have produced water reed for thatching since before recorded history. The reed beds that line the waterways regenerate annually, each winter's harvest followed by spring regrowth, an infinitely renewable resource requiring no planting, no fertilization, no cultivation beyond periodic management to prevent woody plants from invading. A single acre of managed reed bed produces enough material to roof a small cottage every year, forever. The reed itself, Phragmites australis, grows to heights exceeding 3 meters in good conditions. Its stems are naturally coated with a waxy cuticle that sheds water. Its cellular structure contains silica deposits that resist fungal attack. Properly harvested and processed, Norfolk reed produces the most durable thatching material in the world. Roofs that routinely last 60 to 80 years before requiring replacement. The harvest happens in winter, after frost has killed the leaves, but before spring growth weakens the stem base. Harvesters work in flat-bottomed boats or on frozen marsh surfaces, cutting reed with specialized scythes in a continuous motion that preserves stem length. The cut reed is bundled immediately, each bundle containing precisely enough material for efficient handling, typically about 30 centimeters in diameter, when compressed by the binding tie. These bundles are then stood upright in the marsh to dry. The air circulation of the wetland environment removing moisture without the mold risk of enclosed storage. A master thatcher can assess reed quality by sound, the ring of dried stems struck together indicating proper moisture content, the dull thud of inadequately cured material warning of future problems. He can assess it by flexibility. Stems that snap rather than bend were harvested too late, after the plant began drawing resources down to its roots. He can assess it by color, the golden brown of prime reed versus the gray tinge of material that weathered too long before harvest. None of these assessments involve instruments. All of them matter. A roof is only as good as its materials, and materials can only be evaluated by someone who has spent years learning to read them. Chapter 6. The Thatcher's Year. Unlike most construction trades, thatching follows seasonal rhythms that cannot be overridden by artificial lighting or climate control. The work year begins in late autumn, after harvest delivers new material, but before winter, weather makes roof work dangerous. November through February is repair season, inspecting existing roofs, replacing damaged sections, adding new coatings to structures due for maintenance. The thatcher works in cold that numbs fingers, in rain that soaks through every layer, in winds that threaten balance on steeply pitched surfaces. Modern construction stops for weather. Thatching cannot. The materials themselves dictate timing. New roof work concentrates in spring and early summer, when days are long enough for substantial progress and weather is mild enough for the extended outdoor labor that thatching requires. A new roof represents weeks of continuous effort. A small cottage might require 200 hours of skilled labor. A large farmhouse might require 500 or more. The thatcher arrives before dawn, prepares materials while light grows, works until dark, then prepares materials for the next day by lantern light. The physical demands are extreme. Each bundle of thatch weighs between 8 and 15 kilograms. A complete roof requires hundreds of bundles, each carried up ladders, positioned precisely, secured with spars or ties. The thatcher spends entire days crouched on scaffolding, arms extended overhead, driving fixings through compacted plant material into underlying structure. Repetitive stress injuries are endemic to the trade. Shoulder problems, wrist problems, knee problems from constant kneeling on hard surfaces. A working career rarely exceeds 30 years before physical breakdown forces retirement. Yet the trade persists. Sons follow fathers. Apprentices serve 7 years or more before achieving independent competence. The knowledge passes through direct transmission, watching, imitating, gradually accepting more complex tasks, because the skills involved cannot be adequately captured in text or video. Chapter 7. The fixings that hold against time. Thatch must be secured to resist wind uplift, gravity sliding, and the constant minor movements caused by temperature changes, moisture cycling, and biological activity within the roof mass. The traditional fixing method uses hazel spars, lengths of split hazel wood twisted into a staple shape and driven through the thatch into underlying battens. A single roof requires thousands of these spars. Their production was once a winter occupation for agricultural laborers, coppiced, hazel cut, split, pointed, bundled for sale to thatchers in spring. The spar itself is a marvel of appropriate technology. Hazel splits cleanly along its growth rings, producing flexible strips that can be twisted without breaking. The twist creates a spring action that holds the spar open during insertion and clamps it tight once driven home. The taper of the pointed ends allows penetration through compacted thatch without tearing. The natural roughness of the wood surface resists pull-out better than smooth metal alternatives. When hazel spars eventually decay, after 10 to 30 years depending on exposure, they leave channels that facilitate drainage and do not corrode surrounding material. Steel fixings, used in some modern thatching, create corrosion halos that stain the thatch and eventually weaken the steel itself through electrochemical reaction with moisture and plant acids. Different fixing methods suit different materials and regional traditions. Water reed, stiff and resistant to compression, typically receives screw fixings. Long steel rods twisted into the thatch mass. Long straw, softer and more pliable, relies more heavily on spar and ligger systems, with horizontal rods called liggers holding the thatch surface, while spars secure the liggers to the structure. Each method evolved through regional experimentation, optimized for local materials, local weather patterns, local craft traditions. There is no single correct method. There are dozens of correct methods, each appropriate to its context, each carrying accumulated wisdom from generations of practice. Chapter 8. The Long Straw Revelation. Before the agricultural revolution of the 18th century, most English thatch used long straw, the intact stems of wheat, rye, or oat, harvested by hand with sickles, threshed by flail to remove grain while preserving stem length and surface integrity. The resulting material was pliable, workable, and arrived at the thatcher's yard still wearing its natural waxy coating, the cuticle that protected the living plant from moisture and infection. Then came the threshing machine. Mechanical threshing increased grain processing efficiency by orders of magnitude, freeing agricultural labor for other tasks, reducing food costs, feeding growing urban populations. But the machines were violent. Drums studded with metal teeth beat the grain from the straw, and in the process, they shattered stem surfaces, stripped away protective coatings, broke long stems into fragments. Machine-threshed straw was adequate for animal bedding. It was useless for thatching. The impact on rural roofing was immediate and devastating. Villages that had maintained thatched buildings for centuries suddenly lost access to suitable materials. The price of hand-threshed long straw, increasingly rare as farmers adopted mechanical methods, rose beyond what ordinary householders could afford. Slate quarries expanded production. Clay tile manufacturers multiplied. Within 2 generations, thatch became a minority roofing system associated with poverty and backwardness rather than practical efficiency. A few regions resisted. In parts of Devon and Dorset, farmers maintained traditional grain varieties specifically bred for thatching quality. Stems longer, stronger, more resistant to the brittleness that afflicts modern high-yield wheat. These heritage varieties produce less grain per acre. They require hand harvesting. They demand traditional processing, but they provide materials that modern agriculture cannot. In the 21st century, these regional holdouts have become the seed stock for a thatching revival. Heritage grain cultivation is expanding. Traditional threshing methods are being recovered. The long straw tradition that nearly died is slowly regenerating. Chapter 9. The fire question. The objection arrives immediately, reliably, from anyone encountering thatch for the first time. What about fire? The concern seems obvious. Dried plant material, open flames for heating and cooking. The combination appears suicidal. Yet, historical fire records tell a more complex story. Medieval villages did burn, catastrophically, sometimes entirely. But analysis of fire cause and spread patterns reveals that thatch was rarely the ignition point, and often resisted fire spread better than alternatives. The physics explain why. Compacted thatch contains minimal oxygen. Fire requires oxygen to propagate. A lit match held against a properly dense thatch surface typically extinguishes rather than igniting the material. The same principle that allows paper to be packed so tightly it becomes fireproof. Thatched roofs that did catch fire usually ignited from interior sources. Sparks rising through inadequate chimney systems, flames from cooking fires in buildings without proper flues. The fire started inside, burned through the ceiling, and reached thatch already compromised by heat damage from below. Modern thatched buildings address this vulnerability through fire-resistant boarding at ceiling level, properly designed chimney systems, and in some cases, fire-retardant treatments applied to the thatch interior. These precautions reduce fire risk to levels comparable with other roofing systems. Insurance data from the UK, where tens of thousands of thatched buildings remain in use, shows fire claim rates only slightly elevated above general building stock, and total loss rates virtually identical. The perception of thatch as uniquely dangerous persists despite evidence. It persists because fire in a thatched building is visually spectacular, flames visible for miles. The entire roof consumed in minutes once ignition achieves critical spread. A tile roof fire is contained, invisible from distance, dramatic only to those immediately present. The thatched fire becomes legend. The tile fire becomes statistic. Perception diverges from reality. Chapter 10. The Biology of Protection. A thatched roof is not sterile. It cannot be sterile. Within weeks of installation, biological colonization begins. Bacteria, fungi, algae, lichens, mosses establishing populations on and within the thatch surface. Modern instinct interprets this colonization as degradation, contamination, failure. Traditional understanding recognized it as protection. The biological community that develops on mature thatch forms a living skin. Lichens and mosses cover exposed surfaces, reducing ultraviolet degradation of underlying plant material. Their root structures, technically called rhizines and rhizoids, penetrate only the outermost thatch layer, binding surface straws together into a more weather-resistant mat without damaging structural depths. The organisms themselves are hygroscopic, absorbing rainfall and releasing it slowly through evaporation, reducing the volume of water that penetrates into the thatch body. Some species produce antimicrobial compounds that suppress wood-rotting fungi and destructive bacteria. The result is a roof that improves with biological age. Fresh thatch is vulnerable. Its smooth surfaces shed water efficiently, but provide no biological protection. Mature thatch, gray-green with colonization after 10 to 15 years, resists weather damage better than new material. The organisms and the plant substrate reach equilibrium, each benefiting from the other's presence. Modern roofing materials cannot develop this relationship. Asphalt shingles shed their mineral coating over time, becoming more vulnerable as they age. Metal roofs corrode. Synthetic membranes degrade under ultraviolet exposure. Only biological materials, thatch, woodshake, living roofs, participate in ecosystems that can enhance rather than diminish their function over time. This is not romanticism. This is material science. Biological systems optimize through interaction. Industrial materials only decay. Chapter 11. The Knowledge That Nearly Died. By 1950, the British thatching trade had contracted to perhaps 200 active practitioners, most elderly, few with apprentices. The craft appeared destined for extinction within a generation. The materials were scarce, the skills obscure, the market limited to eccentrics and preservationists. What survived? Survived through stubbornness, individuals who refused to abandon family traditions despite economic pressure. Communities that maintained thatched buildings despite insurance difficulties and social stigma. A handful of heritage advocates who recognized what was being lost. The revival began slowly, accelerated by unexpected factors. The energy crises of the 1970s made thatch's insulating properties economically relevant again. Heritage tourism created demand for visually distinctive buildings. Environmental consciousness elevated sustainability concerns. By 1980, the trade had stabilized. By 2000, it was growing. Today, approximately 1,200 professional thatchers work in the United Kingdom, maintaining an estimated 60,000 thatched buildings. Similar revivals have occurred in Germany, the Netherlands, Denmark, Ireland. Wherever traditional thatching regions retained enough buildings to justify specialized trades. But revival is not recovery. The knowledge that survived the 20th century's near extinction is partial. Regional variations that once distinguished Norfolk work from Devon, work from Yorkshire work, have blurred as thatchers trained in generic methods rather than local traditions. Material sources have consolidated. Most British thatch now comes from a handful of specialized suppliers rather than the distributed agricultural production that once served local needs. The deep knowledge, the understanding of why traditional methods worked, not just how to execute them, was carried by practitioners who died before anyone thought to systematically document what they knew. Modern thatchers work competently. Medieval thatchers worked with accumulated wisdom we can no longer fully access. Chapter 12. The Economics of Permanence. A new thatched roof costs between 3 and 5 times more than an equivalent tile or slate roof. The initial investment appears prohibitive to modern economic thinking, which heavily discounts future value in favor of immediate cost minimization. This thinking is mathematically flawed. A tile roof in the United Kingdom requires complete replacement every 40 to 60 years. Replacement cost, at current prices, ranges from $15,000 to $50,000, depending on building size and complexity. Over a 200-year building lifespan, tile roofing requires 3 to 5 complete replacements. Cumulative expenditure of $60,000 to $250,000. A thatched roof requires partial recoating every 20 to 30 years at a cost of $8,000 to $20,000. Complete base replacement occurs every 60 to 80 years at $25,000 to $70,000. Over the same 200-year period, cumulative thatching expenditure ranges from $80,000 to $180,000, often less than tile despite higher unit costs, always providing superior thermal performance during the intervals between work. The comparison becomes more favorable when energy costs enter the calculation. A thatched building requires 30 to 50% less heating energy than an equivalent tile-roofed structure, depending on ceiling insulation standards. At current UK energy prices, this difference represents $500 to $2,000 annual savings. Over 200 years, energy savings alone could exceed $200,000, potentially covering the entire thatching cost, while leaving the building owner with a more comfortable, more sustainable, more valuable property. Modern financial analysis ignores these calculations because modern financial analysis operates on timescales of years, not centuries. Quarterly returns matter. Generational returns do not. We build for immediate profit and accept perpetual cost. Our ancestors built for perpetual benefit and accepted immediate investment. The mathematics have not changed. Our values have. Chapter 13. The ecosystem that roofs create. A thatched roof is habitat. Within the thatch body, protected from weather extremes and predators, dozens of insect species establish populations. Beetles, moths, flies, spiders, an entire food web compressed into a few inches of dried plant material. Birds nest in thatch edges and ridges. Bats roost in the air spaces beneath poorly sealed eaves. A comprehensive survey of a single Norfolk thatched roof in 2008 documented over 140 invertebrate species, including several considered rare in the broader landscape. This biodiversity is not incidental. It is functional. The invertebrate community that inhabits thatch includes predators of wood-boring insects, parasitoids of pest species, decomposers that process shed biological material before it can accumulate and retain moisture. The ecosystem services provided by these organisms contribute to thatch longevity in ways that scientific research is only beginning to quantify. Modern roofing systems are biological deserts. No organism can inhabit a sheet of asphalt or a panel of steel. The insect populations that might naturally control wood pests find no refuge. The birds that might nest find no substrate. The building becomes isolated from the ecological systems that surround it, dependent entirely on human intervention for maintenance and pest control. The contrast extends to end-of-life considerations. A thatched roof, when finally replaced, produces only compostable waste, plant material that returns to soil within months, releasing nutrients that support new growth. A tile roof produces ceramic fragments that persist for millennia. An asphalt shingle roof produces petroleum-soaked material classified as hazardous waste in many jurisdictions. The thatch participates in cycles. The industrial materials terminate them. Chapter 14. The Future That Remembers. In 2019, researchers at the Technical University of Denmark published a comprehensive analysis of thatching as a carbon sequestration strategy. Their findings reframe the entire material category. Growing reed and straw absorbs atmospheric carbon dioxide through photosynthesis. Harvesting the material and placing it on roofs locks that carbon into long-term storage, not permanent, but measured in decades, rather than the weeks or months of decomposition in unharvested conditions. A typical water reed roof contains approximately 15 tons of sequestered carbon. Across the estimated 100,000 thatched buildings in Europe, this represents 1.5 million tons of atmospheric carbon, removed from circulation and stored in functional building components. The calculation improves further when replacement cycles are considered. Every 25 years, a thatched roof receives additional material. The old material, compressed into the roof base, remains in place. The carbon it contains stays sequestered. New growth replaces what was harvested, absorbing additional carbon. The system becomes a rolling carbon sink, each generation of thatch capturing new atmospheric carbon, while previous generations remain locked in the roof structure. Modern roofing materials offer no comparable benefit. Their manufacture releases carbon. Their installation releases carbon. Their maintenance releases carbon. Their disposal releases carbon or creates permanent waste. At no point in the material life cycle does atmospheric carbon reduction occur. The contrast is absolute. Thatch removes carbon from the atmosphere and stores it. Industrial roofing adds carbon to the atmosphere and creates waste. If climate stability is a priority, and the scientific consensus insists it must be, then material choices that seemed economically suboptimal become civilizationally essential. Chapter 15. The Hands That Remember. In the village of Cockington, Devon, a man named Colin McGee practices a craft his family has maintained since parish records began documenting occupations in 1598. 14 generations of McGees have thatched roofs in this corner of England. The tools Colin uses, the legget for dressing surfaces, the needle for securing fixings, the shearing hook for trimming edges, are not replicas. They are the actual tools his great-great-grandfather used. Worn smooth by a century of hands, but still functional, still preferred over modern alternatives. Colin learned the trade the way his ancestors learned it. He spent years watching his father work before being permitted to touch materials. He made mistakes and was corrected. He gradually absorbed knowledge that cannot be transmitted through instruction alone. The feel of properly compressed thatch, the sound of a spar driven to correct depth, the smell that indicates moisture problems developing within a roof body. He worked alongside his father until his father's hands could no longer grip the tools. Then he worked alone, and now he works alongside his son, transmitting the same knowledge through the same methods across the same landscape. Modern construction does not value this continuity. Modern construction values efficiency. Measurable inputs producing predictable outputs, workers interchangeable, skills standardized, knowledge captured in manuals rather than hands. This approach produces buildings quickly. It does not produce buildings that last. The McGee family has thatched the same buildings for 400 years. The roofs they laid in the 18th century are still in service. still maintained by descendants of the original craftsmen, still performing exactly as intended. No modern construction firm can make equivalent claims. No modern construction firm expects to exist in 400 years. The knowledge that survives is the knowledge that transmits across generations. The buildings that survive are the buildings that communities commit to maintaining across generations. Thatch requires this commitment. It demands relationship between craftsman and material, between building and community, between present action and future consequence. Chapter 16. The rain that falls on memory. There is a cottage in the Somerset levels, not far from where William Carew watched the 1990 storm prove his roof, that has been continuously occupied since 1289. The building has no historical significance. No famous person lived there. No important event occurred within its walls. It is simply a cottage, a small agricultural dwelling built to house a family that worked the surrounding land. For 735 years, families have been born under its roof, have raised children under its roof, have died under its roof. The current occupants are the 43rd documented household in the building's history. The thatch above their heads contains material from every century the cottage has existed. Core samples taken during conservation assessment in 2012 revealed stratified layers, medieval wheat straw at the base, early modern rye above it, Victorian long straw higher still, 20th century water reed at the surface. Each layer was applied by hands that are now dust. Each layer protected families whose names survive only in parish registers. Each layer represents a decision to maintain rather than replace, to invest in a building that would outlive the investor. Modern construction does not think this way. Modern construction assumes buildings are temporary, assets to be depreciated, replaced when economically convenient, demolished when land values justify redevelopment. The average American house lasts 50 years. The average British house lasts 80. These are not long periods. These are barely 2 generations. We build as if permanence is impossible and therefore not worth pursuing. We build as if our grandchildren will want different buildings anyway. We build as if the future is someone else's problem. The cottage in the Somerset levels stands as accusation. 7 centuries of continuous habitation. 7 centuries of families sheltered by the same walls, the same roof structure, the same commitment to maintenance that prioritizes longevity over convenience. The rain that falls on that roof today falls on memory, on the accumulated labor of 40 generations, on the material evidence of what humans can build when they build to last. Inside, a family eats dinner. Outside, the thatch does what thatch has always done. It breathes, it insulates, it sheds water, it endures. The storm comes, as storms always come. And when it passes, the roof remains, not because thatch is invulnerable, not because medieval methods were superior in every measurable way, but because someone, in every generation for 700 years, decided that this building was worth maintaining. That decision, renewed by every generation, implemented through craft knowledge passed from hand to hand, is the true technology. The thatch is only its expression.
Archaic resilience.